This lecture will discuss two-sample hypothesis testing. So we're going to build on what we've already done with one-sample tests, but what I've noticed a good number of you were tempted to do is you were tempted to compare two samples together, which is the way we think. We're used to comparing A to B, male to female, Republicans to Democrats type stuff. So two-sample tests allow us to pull two samples and compare some value from each of them to one another. You can do this test for means or proportions. The way these tests work is we use the difference between means. So we're mainly seeing how similar are these two samples. If they're the same, then we would conclude that they're not different at all. But if they're not the same, then you could do a test to see how different they are. We also need to address sampling distributions again. For now, if you have, or what we've already covered, if your sample sizes are large enough, you can assume the normal distribution. If your sample sizes are not large enough, you would assume the t-distribution. Hypothesis testing has the 3 steps that we've already discussed. Step 1, define the hypothesis. Step 2, calculate the test statistics. Step 3, state your conclusions. So we're going to start off with a test for the mean where both sample sizes are large enough to say that we could do a z-test. Now there is a two-sample test template in Excel, and you could grab that and pull that out if you like. But you'll notice it's set up pretty much like the other one, but you have space to put input data for 2 different samples. This template will actually work for either a z-test or a t-test, since now you know when to do each kind. So let's just jump right into step 1. Step 1 is the same. We'll state the null and the alternative. You could have a one-tail test or a two-tail test, same as before. One-tail tests show direction, two-tail tests do not. For this example of one-tail test that we have, on the left, the alternative says that mu1 is smaller than mu2. That could be something like female IQ scores are smaller than male IQ scores. Or, on the right, the one-tail test where mu1 is bigger than mu2, male IQ scores are bigger than female IQ scores. For that two-tail test, that would be one of those same different kinds of tests. The null would mean male and female IQ scores are the same, or gender has no impact on IQ score. You seem to have been comfortable setting up or determining whether a test was one-tailed or two-tailed. Since these tests are based on the difference, you could actually rearrange those hypotheses to show off this is actually a comparison of how different is group 1 from group 2. And what the test is going to do is the test will compare the difference between the samples to 0. So now we're in step 2, which is pretty much the same as before. If you think back to what we were doing, we would calculate sample values and critical values. So the first value that we calculate is observed, where we standardize our sample data. And this is set up the same way. You're still going to use that standardized function. You're still going to need a sample value, a hypothesized value, and standard error. This round, our sample value has to pull in information from both samples, so that's where we calculate the difference. Our hypothesized value is, if you go back to our hypothesis statement, you'll see that when we calculate the hypothesized difference, it's actually 0. If you look in the alternate version of the hypothesis statement where we compare the difference to 0, that's why we do that, so we could see what is the difference we think is there. We are comparing the difference to 0. So when we get here and calculate that hypothesized value, we're just going to type in a 0. And then there's a standard error calculation that's pretty much the same as what we did before, but again, now you have to pull in both sample sizes, and no, that calculation isn't very challenging, but it's already in the spreadsheet for you. Now Z critical, exactly the same as before, no difference there. P-value, same thing, exactly the same as before, no difference there. And they're also already calculated for you. So then we'll move on to step 3, where you compare the absolute value of observed to critical. If observed is smaller, your conclusion is not to reject the null. If observed is bigger, your conclusion is reject the null. You could do the same thing with p-value. If your p-value is smaller than alpha, that's when you want to reject the null. That's when you have evidence that says my data is more significant.